points we're talking about were there's some ideas or principles you could use to get you going, but these principles are in effect all sort of overridable. You can, as we'll go through, you could think there might be something better to do in a particular situation, because the overriding principle is your models of H1 and H0 depend on your scientific judgment of being a good representation of the situation. And that's really the one principle, if you like, the most important one. So although I generally use a distribution which has a mode on 0, you don't have to do that. If in a particular situation you thought if there is an effect there, it's going to be a big one, but there's some reasonable doubt about whether it might be there, and that's why you're doing a hypothesis test, then you could have a representation like this. So I also said and illustrated that if the plausible maximum is about twice the scale of the effect, use a normal, and if it's more like an order of magnitude of 10, you could use a Cauchy. You can turn this around the other way, and let's say what you had been able to put your finger on is some estimate of the maximum. Well, then, as I said before, you could use a half normal with a standard deviation set to half that maximum. But you could also use a Cauchy with a scale factor set to 1/7 of the maximum. Now, this would make a difference. So let me consider a case where we can compare the uniform, which I'd spoken about, where you can put your finger on the maximum, a half normal, and a half Cauchy. So let's say you're interested in proportion correct. 0.5 is, let's say, some chance baseline. So the effective range of the scale is from 0.5 to 1. There's a hard maximum of 1. People can't get more than 1 correct. So some scales have a maximum built in, like if you have a 0 to 7 scale, a change of 7 is a hard maximum built into your scale. Now typically when you use a hard maximum like that, and you use that as your maximum, so uniform going up to that, that becomes a very vague theory. Probably vaguer than it should be, but let me show you. What we could use is a uniform. I'll show you half normal, half Cauchy. Now on my calculator, and I use this example to illustrate that, it always assumes the H0 value is 0. So if you have a case like this, where the H0 value is 0.5, just subtract 0.5 from all of your data points. Because then that resets H0 to be 0. So now what you would have is a scale that goes from 0 to 0.5, where 0 is chance and 0.5 is now the hard maximum there. Okay. So just bear that in mind when you use my calculator. It assumes the H0 value is 0, and that's fine as long as you know that, because you can just subtract whatever the actual baseline is from the numbers. So we could use a half normal with a standard deviation of 0.25. All right? In other words, the standard deviation is half the range you can go up to. Or, by the same logic, you use a Cauchy with a scale factor of 0.5/7. What's the difference between? Now, there is a difference, quite a difference, between the half normal and the half Cauchy in this case, because the half normal really spreads your plausibility pretty much over the whole range still, relatively uniformly, whereas the Cauchy lumps it around 7 to 10%, and then there isn't much plausibility beyond that. So what you could do, let's say you have a task where there's some proportion correct or looking time or something like this, and you feel you have very little idea about what the effect would be in this, what proportion correct or proportion looking time would be in this particular study. One thing you can always do is use the half normal. And remember, if you use the half normal, you think that the proportion, there's reasonable plausibility almost all the way up to 100% one way. If you use the Cauchy, you'll be saying there's a mass of probability around 50 to 60%, and then it becomes pretty thin after that. So if all you could do was make a judgment between one of those two things based on general knowledge, you could then use simplicity just to pick a half normal or a half Cauchy. It would be better if you had some estimate of the sort of effect you'd expect if there should be one here based on past studies, but you don't always have that. So this is something you might consider. So let's say here's 0 to 0.5. This is the data you actually get, 55% correct. So that would be 5% above the baseline. 0.05 in other words in terms of proportion above baseline. That's just significant. How could we model our predictions? Well, this is the vaguest thing you could do with my base factor. You just have it uniform from the null value all the way up to the maximum possible value. Okay. And I notate that as a U for uniform, and I'll give the interval in square brackets there. You could have a half normal with the standard deviation of 0.25, and as you see here, yeah, it is more, smaller values more likely than bigger values, but there's reasonable plausibility all the way up. Or a Cauchy, and that really puts most of the probability between about, well, this would be 50% to 60%, and then it thins out considerably after that. Does that make sense to everyone? Any questions? So I don't know what your predictions would be for the relative base factors in this case. So our data actually falls, 55% is around about here, okay, this value. So it's fairly near the null value of 50%. And what you get is for the uniform, base factor close to 1. So you see, even though this is significant, that'll be just p less than 0.05, the base factor says insensitive in this case. Because this is a really vague theory, and Bayes will punish you for having a vague theory. This predicts a little bit better, so it's now the other side of 1. But when you use the Cauchy, and you said really values around 50% to 60% are most likely, you're rewarded for predicting in advance that the values are going to be quite close to 50%. So it does make a difference. I tend to avoid these really vague ones as much as possible, because often we really can say that the value will be closer. I mean, even if you haven't used these exact materials before or something, and this is some looking time, you might know from experiments with children that these sorts of materials, these sorts of tasks, it will be more persuading that way. If you really didn't know, you're welcome to keep it vague, but if you do have information, it's best to use it.
I'm just trying to, so the 7 times as big part, sorry if I'm with the Cauchy, that's factored into that distribution.
Yeah. So that came here, because from 0 to 0.5 is a width of 0.5, so the maximum is 0.5.
Oh,
so I've divided that by 7 to get the scale factor. So I use that to illustrate a couple of things. The vaguer your model of H1, the harder to get evidence for it, which is, I think, as it should be. If you have a vague theory, it should be harder to support it. And conversely, I'd say if you want to argue for H0, so if this was a case where you wanted to say children or whoever can't do the task, I'll try and avoid the uniform as much as possible, because you've loaded things in your favour of your conclusion, so it's less compelling then when you get a result that's comes from being overly vague. So this leads me to another point. So one thing that's clear from that is it does matter what your model of H1 is, okay? Which is both the blessing and the curse. It's the curse in that you have to think carefully about it, and it's a blessing because, of course, any measure of evidence worth a salt should depend on your theory. There's no such thing as evidence for a default theory. There's only evidence for particular theories. But some aspects of the way you model your H1 are going to be somewhat arbitrary to you. And so it becomes important to establish how robust your conclusion is to changes in assumptions. So a robustness check is how does the conclusion hold up for implementations of same or similar scientific judgment. So robustness doesn't mean your conclusion holds for any model of H1. Robustness means the conclusion holds for any model of H1 that respects your scientific intuitions about the situation, or reasonable scientific intuitions. I'll illustrate that. So go back to the meditation study. There's the original study. You do walking instead of breathing, and you get an effect that if we model with a half normal, using the original study as the standard deviation, gives us a good Bayes factor in favour of the intervention. But now we could ask, and this is how robustness checks are typically done, say on JAS, you take the same type of distribution, say half normal, and then you change the scale factor to see how much the conclusion depends on the particular value of the standard deviation that you've put in. So what you can do is to find the smallest standard deviation where you just miss out on there being substantial evidence, and the largest standard deviation in which you just miss out. And these are the values for this particular case. Now let's think about this particular case. We have a change in mindfulness ratings of 3 to 3.6 in the original study. Okay. So a change of 0.6, which is why we put that in here. Now in this model, we have to go down to 0.07, below 0.07, before we lose the effect. So we ask ourselves, what does that mean, 0.07? Well, twice that is a bit over 0.1. So what we'll be saying with that model is the maximum change in mindfulness that's scientifically plausible is 0.1 rating units. Now, surely it's scientific judgment. If the original study got 0.6, our maximum is not 0.1. That's much smaller than respects our scientific judgments, you see. Surely we think, even if 0.6 is a bit of an overestimate, it's still possible. And on the maximum side, we have to go above 2.5 units. So that would be a change from 3 to 5.5, which is off the scale. Or in terms of maximum, the maximum change would be 5 units, would be 3 from 8, which is off the scale. So this model also no longer respects reasonable scientific judgments. See what I mean? So that means our conclusions are robust. It doesn't matter the precise scale factor, we're going to conclude there is good evidence for meditation here. Because we have to change the scale factor to such an amount that it's no longer scientifically reasonable to hold such a model. So to reiterate, the question isn't are there some models in which the conclusion fails, but are there some models which still respect scientific intuition where our conclusion changes? That's the issue.
So is this something that you report in papers when you report Bayes factors, like the range of
Yeah, now I haven't done this.
H1s over which they hold?
Yes, now I haven't done this so far. I've just sort of justified a model and then gone with what that said. But what Balázs Axel suggested to me, a chap from Budapest, is why not report, say, a robustness region. So every time you have a Bayes factor, you give, so in this case, that would be the change of scale factors. That they then tell people how robust the conclusion is to the change in the scale factor. I think that's a good idea, actually. So that is something to consider putting in. As I say, I haven't done that myself, but I think it is a good idea and something I probably will start doing. Yes.
So, just to go over again, so you've effectively, before you conduct the Bayes factors, you would specify how you're going to model your alternative, like H1.
Yes, that's right.
And then once you've calculated that, you almost reverse engineer to find out what this isn't done in advance, this is done after you've calculated
It's the robustness
the
region,
robustness.
that's right. Yes,
Yeah.
that's right. Yes. So I think that would help mollify some of the concerns about the sensitivity of your conclusion to your precise model of H1, or to the prior, in other words, if you showed how robust it was. So I think this would be an easy way of doing it, which wouldn't take up a lot of space, doesn't require big discussion, you can just put that in. So, principle, robustness. Is the conclusion robust to changes of the model that reflect the same scientific judgment? And one simple way of implementing that would be say, what range of scale is actually scientifically plausible, considering that, and putting in that robustness region. So here's another example. Let's say you have theory A that says autistics will perform worse on a task than controls. But you have another theory that says they'll perform the same on this task. And these are the data. Autistics perform 8% above chance with this standard error, and controls 10% with this standard error. So this effect here is actually just significant. The controls performing above chance, and this one will be non-significant on the t-test. But on the t-test, on the difference between the two, it's non-significant. Now, it's important to establish whether there is an effect or there isn't an effect, because we're going to pick one or two theories depending on that. Now, you know, based on what I've said so far, that we can't use non-significance as a basis for saying no difference. This could be insensitivity, could be evidence for no difference. So how should we model H1? You might say, well, there's no prior study I can refer to here. This is sort of new. So I know what I'll do. I'll just use the default base factor that a lot of packages give you. The default base factor, say JASP, and on the Rauder base factor page is a Cauchy with a scale factor of 0.7. And the scale factor there refers to a Cohen's d, so it means Cohen's d of sort of scale effect you're thinking of is Cohen's d of 0.7. That's okay, that's reasonable. 0.7 is close to 0.5, different sort of effect size. So we'll just do a default. I put this as JZS because they call that the JZS space factor, the Rauder one or the one by default in JASP. 0.27. By the way, when you do a default, say, base factor, do report what it is and do report the scale factor even if it's given as a default. Now, 0.27, do you remember what that means? Support for the null. So on the face of it, this looks like evidence for theory B and against theory A. Now, so if this is a situation where you'd use a default base factor, well, if any situation is a situation where you use a default, maybe it's this one where you have no real ground in past studies for predicting precisely what the effect size will be. But actually, often, your own study contains constraints within it that inform you about what you can expect. Because on theory A here, the difference cannot be more than 10%, right? We already have a constraint built in here that if the controls are performing at 10% and the autistics perform worse, the difference between the two could be 0 if they're performing at 10%. But if the autistics go down to 0%, the difference would be 10%. But that's the biggest difference you can possibly get. So there's a constraint already built in here. So if you think of 10% as roughly a maximum difference you could expect, we can model that with a half normal, with a standard deviation of 5. Otherwise, things are still pretty vague other than that. And then we get a base factor of 0.94, which says it's insensitive. So using information and constraints that are actually already in your study, I think the legitimate conclusion here is actually no conclusion should be drawn yet. The data are insensitive. Because what you're in effect assuming with this one is the difference between these two could be unreasonably large. That was the problem with this. But unless you actually think through the effect sizes in your study, you can miss these sorts of things. Because we as researchers haven't been used to thinking about effect sizes. So it's easy for us to be a bit glib about this. Now, one thing I'll say about the default here is this was 0.7 was suggested by Richard Moray. But if you ask him why 0.7, he didn't mean you should always use 0.7. He said, this is just the value that happened to be close to the value that is often used in my lab, or that of his wife, so we put it in there as close to a useful value. I never meant you should just take this off the shelf and just use this all the time. Like I'm telling you, he says it's your responsibility to decide what is the effect size that's actually reasonable in your study. So there's no disagreement here between the sort of different base factor aficionados. So principle is use other estimates or some objective constraints to set scale of effect. Yeah.
So in the, if you could go back to the previous slide.
Yeah.
So you were suggesting saying 10%, then it can't be bigger than 10%.
Yeah.
Because in my head, before you put it up, I was thinking, oh well, 9% right is the mean. So you could is the grand mean.
Yes,
So you
you
work
could-
it out on the basis of that. So
Yes.
So I'm not. That's what I would have done before you said that. So
Yes. And then you've got a standard deviation of 4.5, which would be very close. And where that would sort of come out in is by putting a robustness region.
okay.
So that would solve that little problem. But often it's reassuring that those two different ways of thinking about it they would produce effectively the same answer. This isn't going to change much, 5 versus 4.5.
No, I mean if the autistics were a lot lower than the controls, obviously it would be more of a difference. But
Yes. Probably I would be motivated to use the controls in this case because we have a theory that they will be the maximum and the autistics
Yeah.
will be less than that. So that's the one that sort of
yeah.
makes most sense to me thinking about it. So now I just want to say something you can't do. So I said use other estimates. Be scientifically informed, in other words. In other words, don't just pull numbers out of the air. But when you model H1, be scientifically informed. I just want to point out one way in which you shouldn't be informed, as it were. So still dealing with this example of mindful walking. Let's say your actual difference you got was 0.2 units, those were your data. And you thought, well, actually, the best estimate I have of what I expect is my very data itself. So why don't I say I use that to inform my predictions, and I'll predict 0.2 units based on the data that I got. So now the problem with this is we're using the very same data twice. We're using the same data to generate the predictions of the theory as to test the theory. So that's double counting, and that is illegitimate from a Bayesian. The maths doesn't go through, as it were, if you're using the data twice in two different roles, one to make predictions, the other to test the predictions. So in this case, we have a theory that meditating on sensations or whatever is going to, for 2 weeks, is going to improve mindfulness. So we have independent means of generating predictions from that theory, namely this past study. So that's what we should be using to test the theory. Okay, now next example to illustrate another point. Let's say, if you're interested in implicit learning or implicit perception, subliminal perception, you're often interested in establishing that there is no conscious knowledge, or in a certain set of materials and certain conditions there's no conscious knowledge, and then you conclude that this was implicit learning or subliminal perception, whatever the case may be. So often what you need to do is to come up with a claim of non-existence for the conscious knowledge case. In other words, assert a null hypothesis, or get evidence for the null hypothesis, in order to claim it was implicit or subliminal. So let's say in this study, in terms of subliminal perception, we do get a priming effect, which is significant, or, as I'd rather say, Bayes factor is greater than 3. So you have evidence for there being some priming, some processing. But you want to argue that this was unconscious processing. You do that because you have a test of conscious perception, which is non-significant. Now you might say, well, I don't know how much conscious perception is relevant here for this amount of priming, so what I'll do is I just use a default Bayes factor, and then in this case that will be 0.16, less than a third. Right? Good evidence for there being no conscious perception. But I just told you, don't pull defaults out of the air. You've got to think about what size effect am I really expecting. So say, okay, I'm going to go and find a study where the claim was that there was conscious perception operating. Or what you need to do is to run your own study where there's conscious perception going on. You don't master the materials so well, or in implicit learning you guide people to look for rules, give them some hints about what the rules are and so on, so you're dealing with conscious knowledge. Because then you can look at the amount of priming that you get for a given amount of conscious knowledge. Okay. And that enables you to calibrate the two tests, you see. So for the sake of simplicity here, I've given the same amount of priming, because then we can say, aha, it's the same amount of conscious perception we expect in these two cases. That's the calibration. All right, so the standardized effect size was 0.8 in this study for that level of priming, and it was done consciously. So we expect 0.8 in this case. And there's JZS 0.8, 0.16. Actually very close to the default. The default's currently 0.7, so they're very similar. So say, now aren't we safe? We didn't pull a number out of the air, we actually referred to a study, or we ran some more data. So often in thinking about what size effect you predict, you might have to collect more data. In this case, in a conscious condition, in order to argue this condition wasn't conscious, because we know what we're looking for if it were conscious, you see. We've run the conscious condition. We wouldn't know what to look for if we're conscious unless we collected data on it being conscious. And this is typically left out of subliminal perception experiments, but I regard as absolutely crucial to know in order to assess whether we're dealing with unconscious knowledge. So you say, aren't we safe now? We've done as you said. But what if I told you that this test involved 100 trials, and accuracy in raw units was 60%. This test involved one trial on the test of conscious perception, and accuracy was 60%. I'm taking this from a true example, actually, not the precise numbers. Well, almost these precise numbers. Well, people tested conscious knowledge with one trial. So now what does that do? That makes your standardized measure, your population value of standardized measure, very small. When you have one trial, you have a lot of noise compared to your signal. Increase the number of trials, increasing the number of signal compared to noise in the population. This isn't just a matter of sample, it's a matter of what the population actually is. But clearly the number of trials you have is theoretically irrelevant. So what strikes me as more theoretically important is the accuracy here, just the percent being correct, was 60%, and the accuracy here was 60%. Those are the comparable figures. So now if we do a Bayes effect on the raw effect size, percent correct, it says this is insensitive. And so it should be, because if H1 is predicting 60% and we have 60%, that non-significant result must be insensitive. Does that make sense? So I have a personal preference for raw effect sizes. A lot of the time it doesn't matter, but in every case I've come across where it did matter, it was the raw effect size that was the better one that you should be using, not the standardized effect size. And notice here how this motivates you. The reason why the paper I'd seen, they used one trial for the measure of conscious knowledge is they wanted it to be non-significant. And so wanting non-significant motivates you to make the test as insensitive and noisy as possible. But so does it if you do a Bayes factor on a standardized effect size. That motivates you to make your test as noisy and insensitive as possible to get a Bayes factor that's low. But if you ask the right scientific question, which is about the raw effect size, it motivates you to make your test as sensitive as possible, as many trials as possible. Otherwise, you're just going to get Bayes factors of 1 back and telling you you can't conclude anything. So. So, principle, use raw effect sizes in preference to standardized. The raw effect size reflects more about properties of what you're trying to measure, states of memory and so on. The standardized effect size is sensitive to things like how many trials you're using, what other factors are in your analysis, like covariance that are taking out noise. Those are properties of your measuring instrument, not the thing you're measuring. So I take it we're sort of realists, and what we're interested in is like the mind, something I'm going out there. And so we want our measures to reflect the thing out there we're interested in as much as possible, which is raw effect sizes rather than standardized. And that can deal with situations where the amount of noise is unknown, like people who do fMRI. I've heard it said, oh, we don't do power calculation because we never know how much noise there is in a given day. Well, then it's hard to take account of the noise if you don't know how much there is. But if you use raw effect sizes, it immediately takes into account any noise that's just sort of superimposed on top of that effect size. So these are the principles which I think are uncontroversial. We'll see when we hammer out a consensus statement, but I think they'll run something along these lines. The overriding principle is that your model of H1 and H0 should be, according to scientific judgment, adequate approximations of the situation. Okay? If you think they're a good representation of the scientific problem, that's what's important. So some assumptions to consider in order to fulfill that principle. Small effect sizes are more likely than larger ones. But you can break it if that's, if the scientific situation isn't going to be well represented by that, then break it. But probably in a situation where there's some doubt about whether effect exists or not, which is when you would hypothesis test, is a situation where the effect size could go from 0 up to some value, and it would be useful to consider smaller values as more likely than bigger values. Don't just use default values. Even in a situation which will be most enticing to use default values, really consider what size effect do we expect here, and use your scientific knowledge, which could be constraints embedded in the very situation and the very data that you have, to inform your model of H1. Bear in mind, if you use a half normal, you're thinking the maximum is about twice the scale factor, and the Cauchy is something close to 10 times that. That's a sufficiently big difference, I think, that you can have a relatively uncontroversial judgment about which of those representations will be best. But fortunately, it doesn't actually matter that much, that particular decision. If theory predicts a direction, then use a half normal. Use raw effect sizes in preference to standardized, and consider robustness. What range of scales is actually scientifically plausible, and for what range of scales does the Bayes factor give you the same qualitative answer? So those are the principles, I think, that should guide and help you deal with any particular problem. So the main message is to show evidence for a point null hypothesis. I don't know any other solutions on the market, actually, other than a Bayes factor, or approximations to a Bayes factor. But bear in mind, when you do that, it's not evidence for a point null full stop, but for a point null relative to your model of H1. Okay? To know whether there's evidence for nothing being there, you need to know what could have been there, right? So your model of H1 needs to be appropriately informed. And what that means is when you write up your Bayes factor, justify why you used the model that you did. It's because this is the effect in that paper. Then people know the basis for the conclusions that follow, and they're free to accept them or dispute them, and they know the objective reasons for drawing any particular conclusion. So what I do in my papers now is have a little preamble before the results section, where I describe why I used the models I did for all the Bayes factors that would follow, and any parameters that are set, what was the basis for setting them. Now, I want to go through the criticisms of Bayes factors. Yes?
Can I just come back to one thing you said before? Just
Yes.
Because, so when you said you must never use the data you've got to...
Yes, it's not quite, not exactly the data, but you can't use the very same estimate that you got to predict that estimate. But you could use other aspects of your data.
So here's a situation that I've seen come up a lot, partly my own data and also editing, where people get, and we were talking about this a lot, they get a main effect, right, for something they're interested in, and they want to say, that, but they don't get an interaction. They want to say this holds for trained and untrained words, or this holds for men and women. And so they get their main effect, and because they don't get an interaction, they conclude it holds for both groups. If you wanted to actually show it holds for both groups, could you use the value you got, the two groups together, and look at each group separately using the value from the whole group to H1?
Yes, so just to repeat a little bit what you're saying to make sure it's on the recording. So this is like this study we were talking about before, where we're using some aspect of the data to inform us. And there it seems entirely reasonable to draw the conclusion that it's insensitive by using some aspect of these data in order to test another difference. So yes, that's often a sort of a quick way of getting out of Bayes factor when there isn't previous information available, is to use constraints within your own data. So as you're saying, you might use and I have used this before, an average effect in order to test the difference between two groups.
Okay. And it doesn't matter that those groups were contributing to the average?
I think you're using the best information that you have. What would be better is to have an independent estimate of that average effect. But that may be a luxury. So if you have that, I would use the independent estimate. But let's say you don't have that, and these are difficult data to get, you know, the children or might have developmental problems or whatever, then I think we need to extract as much information as we can from those data in order to draw reasonable conclusions. So these are some of the criticisms of Bayes factors. If you know any other criticisms, then shout them out now, and we'll deal with them. But I think that these cover what I've come across. This is sometimes called a sensitivity to prior. Okay, so your conclusions just depend on your prior, or your model of H1. I've been saying. People sometimes criticise default Bayes factors. So the default Bayes factor is not relevant to your theory. They might say the point, and this is often used as a criticism against all hypothesis testing, including significance testing. The point null hypothesis is never true, so why you bother testing it? And the criticism can be the Bayes factors don't control error rates. And surely we don't want to make errors, we'll keep error rates low, so if they don't control error rates, isn't that a problem? So let's go through those. So in a way, I hope you already have the answer in your head for this one. Different models of H1 give different answers. Well, of course they do, and so it should be. Different theories make different predictions. So obviously the evidence will be different for different theories. That's the way any measure of evidence should be. Or as Jeffrey said, it is sometimes considered a paradox that the answer depends not only on observations but also on the question. It should be a platitude. So what this highlights, it's important to specify why you're using the model of H1 that you are. Which then brings us to the next one, is the default Bayes factor is not relevant, or not necessarily relevant to your theory. I say, right, quite correct. Make sure your model of H1 is relevant to your theory. And there may well be the default value, a Cauchy might seem reasonable enough to you with a scale factor of 0.7, but you have to consider that and justify it. So in other words, a justification for using a default Bayes factor isn't that this is the default that JASC gives me. The justification is that effect sizes around Cohen's d of 0.7 is what's typical in this area. So the corollary of that is always specify what your model of H1 is and give an objective reason for why you used scale factor of 0.7 or whatever it is. Now the point null is never true. Therefore the only thing to do is estimate. In other words, you can never make a type 1 error because at least if you go down to the quantum level, the point null is always false. There's always some effect there. So testing the null hypothesis is this pointless activity that people become obsessed with. So I think a good counterexample to that comes from Tom Baguley's textbook, Serious Stats, which I think is a good book. If anyone wants some bedtime reading for statistics. But he gives this example from an online ESP experiment, extrasensory perception. In other words, can one mind communicate with another, not through the conventional sensors? So there's a chance baseline of 50%, and after running nigh on 30,000 participants, the confidence interval was 49.6 to 50.2. So now, my and Tom's view of this was amazingly tight interval around 50%. So it's, you know, so the true null. What is the true null? Maybe it's not exactly 50% to the billionth decimal point, but it is 50% plus or minus 0.3%. And maybe if they had run 60,000 or more, you know, we could see where that is as that interval shrinks more and more. But it's definitely within minus 0.3 to 0.3%, around 50%. Okay. But now, the good thing about Bayes is that this we can use any model we want. If we wanted to use an interval null hypothesis, we can do that. In fact, I could show you how to do it on my calculator. So let's take a result that's just significant. It's 55%, correct? P just less than 0.05. Using a half normal, and let's say 5% was the order of effect that we're expecting here. So we get a Bayes factor of 4.27 against the point null. Well, if the if plus or minus 0.3% contains the true population value in there, plus or minus 0.5% definitely does in that circumstance. So I've used the interval null. So the null hypothesis I've represented as a uniform going from, in effect, 49.5% correct to 50.5% correct. Okay. And now we get a Bayes factor that is virtually the same. So my conclusion is the point null will often be a perfectly adequate approximation in well-controlled experimental research. That's not guaranteed to be always true, but I think when you're counterbalancing materials like this is, and you have a controlled experiment, point null will be a good approximation. The other thing I'll say about that is, as scientists, unless we're doing elementary physics, we're only ever interested in approximations. We're only interested in our theory being approximately true to whatever the limit of accuracy of our area is. So these statisticians who say, oh, the point null is never true, well, neither is this normal distribution you assumed for your data, neither is that linear trend that you assumed for your data. All our models are only approximately true, and the point null is in no way exceptional in that case. So my conclusion is the point null is perfectly fine. It's a good approximation for much of the study we'll do as experimentalists. Doesn't mean it'll be always true though. And in an area of big data where you might be getting hundreds of thousands of people, then it may well be useful to put in interval nulls in your Bayes factor calculator. But I will say, well, that's a problem for significance testing. It's not a problem for Bayes factors. You just put in the interval null in your Bayes factor. So let's go on to a Bayes factor does not control error rates. That's right. The Bayes factor fixes strength of evidence. Remember, that's how we started with measuring strength of evidence. And what you do with evidence over many cases, that determines your error rates. So evidence is one thing, and the precise way you make decisions is another. So fixing one does not absolutely determine or fix the other. So in this case, if I'm interested in who stole the cakes, well, there's the evidence. Okay. Now, that evidence remains the same, regardless of my decision of whether we should punish this poor fella here or not. And our decision to punish depends on various non-evidential factors, like how we feel when we look into his eyes. Okay? That's quite separate from the evidence. But that's what error rates depend on. Now, I think there's an implicit presumption in people who talk about error rates that if you found the error rates were, type 1 error rates were, say, more closer to 10% than 5%, that should change how seriously you take the conclusions that you're drawing from Bayes factors. But hang on a minute. The amount by which you should change your opinion in H1 versus H0 is completely determined by the evidence, not by error rates. That's how we started in deriving the Bayes factor. As long as you accept the statistical assumptions that went into the Bayes factor, like normal distributions and so on, the Bayes factor tells you how much you should change your confidence in H1 versus H0. Error rates do not tell you that. Error rates depend on non-evidential factors like your criterion for making decisions. But it's not as if the two are independent. What Bayes factors do is they minimise the total errors. When you use Bayes factors to make decisions, you're minimising the sum of type 1 and type 2 errors. To put it another way, the bigger the evidence, the smaller the errors that you make in different situations. But an error rate is a bit like shining light on the evidence, and that casts shadows, where the shadows are the error rates. As you look at the evidence or shine the light in different directions, you cast different shadows. You can have errors going a bit more one way or the other way, but the evidence is still the evidence. And if you're at all worried about total error rate, what you should do is increase the amount of evidence that we accept before drawing conclusions. And I do think the amount of evidence represented by Bayes factor of 3, in other words, p less than 0.05, is rather on the low side. And I do think, as I said before, the best way of thinking about a Bayes factor of 3 or p less than 0.05 is it means could be something going on here, worth having another look. But if we wanted to draw some more definitive conclusion, we're talking about Bayes factor of 6 or 10. But that will be a discussion that we have as a community later. So I conclude that by saying there are no arguments against Bayes factors, only about their misuse. So as long as you understand what you're doing and use them appropriately, but you in the end have the guarantee of the axioms of probability that you are getting evidence for the one thing versus another. Okay, that was really what I wanted to say. So the main summary would be to obtain evidence for a point null hypothesis, you must use Bayes factors. And so one moral, even if you never use Bayes factors, is never just on the basis of non-significance, say there was no effect of gender or people were at chance. Okay? If all you're going to do is significance testing, just report something was non-significant, but don't draw any conclusions from that, and don't discuss why that might be. Just say it was non-significant, and then that's the end of the story. But obviously you might want to say there was no effect there, well then you've got to use Bayes factors. I'll just skip over that. Just go through these calculators again in light of what I said. So this one, my calculator from my homepage, you use uniform or normals, raw or standardized effect sizes, and you can center on 0 or elsewhere. So I find that generally useful. This one, the Singe one, it does all of that, but also puts in count Cauchy and T distributions to model H1. And you can use it when Flash is not running on your computer. And then the Rauder and Richard Moray ones just use Cauchy, it's just standardized effect size and centered on 0. But they can be convenient to use if that's what you're interested in. And of course, JASP is now becoming more and more prominent and will continue to improve. And everything it does well. So as it's added to, if it doesn't do what you want now, sort of keep looking out for it because we'll add to it. Now it does do, one reason I didn't use it for a long time is it didn't do transforming variables data manipulation. Now it does do that. Sort of seamlessly, it jumps out of JASP into your data editor, but then when you make a new variable or transform it, it's automatically changed within the JASP environment. They just had just been doing Cauchy. It now does uniform, No, now does normal and t-distribution, which doesn't have to be centred on 0, which it used to be before. The only problem for me is, at the moment, it only deals with standardised effect sizes. And as I say, I really much prefer raw. Raw will be in there in a few weeks. Okay, so just keep an eye out for that, and that will be there. So that's all I have to say in terms of my talking bit. Deal with any questions.